Our second algebraic method for solving systems is often referred to as the elimination or the addition method. Now, the ending to this system solution process is very similar to substitution. There will be a small difference in how we start out and the way that we eliminate one of the variables. And in this case, what we're trying to do is identify or create a pair of terms that have the same variable and coefficients with the same magnitude, but they have different signs. For example, if I have 2x in one equation and negative 2x in the other equation, if I go to add these two equations together, the x values will cancel out, leaving me with only the y values. Same as if my y values have opposite signs, but same magnitude. So if we don't have that to start, then we need to rewrite the equation by using some multiplication to manipulate one or both of the equations. Once we've done that, then we're going to go ahead and add them. There are some schools of thought where you can subtract and you don't need different signs. You can just have the same coefficient, and that is a completely valid process. But I'm going to focus on the addition way to evaluate it. I think it makes it a little bit more clear, but you're free to do it as you please. Then we solve the equation and we substitute the value in for the variable that we find, just like we did with substitution. So let's look at a first example, and we first want to identify, do we have a matching pair of opposite coefficients? Well, if I look at my x terms, I see that one is a positive x and the other one is a negative x. Those are already opposites. So I can go ahead and start by just adding these two equations together. Well, if I take x plus negative x, I end up with nothing. But if I take negative 5y and I add y, I end up with negative 4y. And if I take negative 12 and I add 4, I get negative 8. Now I have my one variable equation for step 3 that we can go ahead and solve. So we divide, and we get a y value that equals 2. Now that we know what y equals, we can substitute it back into either of the original two equations. I'm going to choose this one. X minus 5 times 2 equals negative 12. And now we have our solution of negative 2, 2. And we could use our other equation here to verify our solution. If we want to go ahead and plug in our solution set here, and we see that this point is indeed on the other line as well, so we know that our solution is negative 2, 2. Now it doesn't have to be x that you eliminate, you could also eliminate y. So just like before, we see that we already have opposite signs here, so we can just start by adding the two equations. 3x plus 5x equals 8x. Our y's cancel, and then we're left with 16. And the value for x is 2. We'll go ahead and substitute 2 back into one of our equations. And now we have our ordered pair of 2, 1 as the solution. Let's go ahead and plug it into the second equation to verify. And we're left with a true statement, so we know that our solution is correct. Now, what if we don't already have a matching pair of opposite coefficients? Well, what we can do is multiply our equations in order to manipulate them so that we get that matching pair. And so first we start by looking at what variable do we want to eliminate. We can choose x or we can choose y. Doesn't matter which one, you choose. And then think about, how can I make these coefficients opposite? So I'm going to just pick x because I can. And I have to think about, well, what can I multiply each of these numbers by to make them opposites? Well, I could easily multiply a 3 and a 4 so that I get a 12 and a negative 12. So I want one of these to be a 12x, and I want the other one to be a negative 12x, so that when I add them together, the x term eliminates, leaving me with just the y term. Which one you multiply by a negative is up to you. I'm just going to do the first one. So in order to get 3 to become a negative 12, I multiply it by a negative 4. And in order to get 4 to become a positive 12, I multiply it by a positive 3. And so we're going to get two new equations. We go ahead and distribute. Don't forget to distribute to the constant term. That part's often left out in these types of problems. So we have negative 12x plus 8y equals negative 40. And then if we distribute the 3 to all the terms, we get a positive 12x minus 9y equals 45. So let's go ahead and add these together. Our x's eliminate, leaving us with negative y equals 5. Therefore, y equals negative 5. So we found our solution just like we did in our previous methods. We can go ahead and substitute it back in to one of these two equations. Let's choose the first one. And we got our x value of 0. So our solution is 0, negative 5. We could substitute it into the second equation just to check that it's right, but I'm not going to take the time to do that now. We've already shown that example on the previous two. So here again, we can pick for D what variable we want to eliminate. If we wanted to eliminate x, what we could do is multiply by the same thing we did last time. We could multiply by negative 4 and a positive 3. That would allow us to eliminate the x. But sometimes what I like to notice is that one of my coefficients already has opposite signs, so I don't have to multiply by a negative. So then I have less chance for sign errors if I forget to switch the sign when I do the multiplication by a negative term. And so what we can do is just think, well, this is already a negative, this is already a positive. I want the same magnitude, so I can easily turn this term into a negative 10 and this term into a positive 10 just by multiplying by the other coefficient. So I can multiply the first equation by 5, and I can multiply the second equation by 2, and that will give me opposite coefficients for my two equations. First one becomes 15x minus 10y is 30, and the second one becomes 8x plus 10y equals negative 16. This time our y terms cancel, leaving us with 23x equals negative 46, and x equals negative 2. We can now substitute negative 2 back into either equation. Let's do the first one. And we just solve. And we get our ordered pair, negative 2, 0. Last couple examples. Here what we can do is we can just actually multiply our first equation by negative 2. That'll turn this term into a negative y, which allows me to cancel with the positive y that I have here. But we should notice something happens that is quite interesting. I would be remiss if we didn't have a question that gave us an interesting result. And so I've just written this underneath here, and you can see now that if we were to go ahead and add these two equations together, well, what's going to happen is that 6x plus negative 6x is 0, and y plus negative y is 0, and 5 plus negative 4 is 1. So we're left with 0 equals 1. Well, just like previously, when we have a false statement and there are no variables remaining, then we know that it is no solution and that these lines are parallel. No solution, empty set. And I bet you can guess what's going to happen next. For this one, let's think about what we can multiply by. Well, these are already opposite, so we just need to double it. Multiply by 2. So our first equation is negative 10x minus 6y equals 18. And when we go ahead and multiply, we get positive 10x plus 6y equals negative 18. And we add these two equations together, and we'll see all three terms cancel. And so we're left with 0 equals 0. we're left with a true statement. And of course, all true statements mean infinitely many solutions, all points x and y, the set of all ordered pairs x and y such that 5x plus 3y equals -9.